first lecture for applied heat and mass transfer. So as mentioned in the tutorial that we said for all the lectures, we try to formally start at 3:10 to give you some time to catch up with each other. And then we will do these formal lectures. And the first thing is a good news that we have the access to Canvas. Yes? Okay. So I've uploaded all these materials required on week 1. So yeah, I've seen many of you already signed up, but for any students, if you want to find some partners and need to sign in anyway, you can leave your message on that sign up link here, on that instruction part, or you could utilize this discussion section to find if someone else also want a partner. And you could see all those things uploaded here. Firstly, weekly slides. And this refrigerant table and chart, you might need this for your tutorial practice. What are you looking for? Yes. So I printed out this for you for the first time, but like next time or in your own practice, if you want this, you have the access here. This is a chart and this is a table. So later we will explain what's, those are basically the same. And for tutorial recordings, normally it will be uploaded to Echo system, but I don't know why, like every semester I cannot do that. So I just manually uploaded it here. So for the tutorial recordings, you can find it here under each week. And we also provided a lot of like study notes to you. For week 1, it looks a little bit scary, but for the first part, it's just the review. So if you're already really confident in heat transfer, then you don't need to worry about this part. And the second part is some practices for refrigeration cycles. So lots of introductions and also practices. And you also have all those solutions provided to you. So these are like some additional materials. If you have the time and also interested in all those applications, how to do the calculations, you could go to these study notes for self-study. Okay, so that's it for Canvas. And also I just counted the numbers. It's like only half of you come, so that means another half is watching the videos. I would say for practices like this, it's better that I show you like step by step how to find the dots. So using DocCam would be much better, but the DocCam in this classroom is not connected to the computer. So that means students watching the video cannot receive these DocCam informations. Okay. Keyboard is not key. Okay, so the second part is refrigeration cycle. Okay, so I believe everyone is already very familiar with some applications like fridge or the split air conditioning system. So you know for heat transfer, we learned last semester, we say that the heat is transferring from high temperature to the low temperature. But now we want to deal with some scenarios. Say in the summer, the indoor is very hot, so we want to absorb the heat from the indoor environment and reject the heat to the outdoor environment. So you will find like indoor is 20 Celsius degree, the outdoor is like 30. How do you achieve that kind of heat transfer from a lower temperature to a higher one? So that's basically what we are going to introduce in terms of the refrigeration cycle. And for the heat pumps, it's just a reversed application. You just set the evaporator and just swap the evaporator or the condensers. So the principles behind these two is the same. So we just taken the refrigeration cycle as an example. So you know with refrigeration cycles, you get ice cream, you get fresh fruit and also vegetables. And not limited on that, in these modern lives, you need this air conditioning for like data center, your residential buildings, and especially for commercial buildings, public buildings. So this is a large amount of demand in this area. And also like for chemicals or medical use, they are quite strict on controlling the temperature of this one. So that means just by looking at all the slides, you can imagine how much job opportunities you can find in the future by just studying this week's content. And so if we know the importance, like we need to keep the refrigerated space at a certain temperature, but the principle behind is actually remove the heat from a lower temperature space and reject to a higher temperature space. So how do we achieve that? And a very simple example would be the very old air conditioner that you see like in the house used in the 70s, 80s. And so this is for residential use. And if you could understand the principles inside here, you could also apply that into some much larger commercial products. For like hotels or hospitals that basically using the same, but using evaporators. So many evaporators in each room connected together and get connected to the compressor, go to the condenser, expansion valve device, and go back again. So that's a larger cycle. But for the very basic or simple example, the old air conditioner, you can see it's still using the evaporator going through compressor, condenser, and expansion device. So now I have a question for you. So say it's the air conditioning system here. So which part is we are looking at? This part. So is this the evaporator part, compressor, or condenser? Yeah, evaporator, and why is that?
It's removing it from the sun.
Yes, so when we say evaporating, something has to absorb the heat. So this thing, this material itself, get evaporated. So every time we are saying evaporator, also evaporating or condensing, we are saying the refrigerant inside this circle. So when the refrigerant gets into the evaporator, it absorbs the heat from like the indoor environment. So the refrigerant itself gets evaporated. So change from the state of liquid to gas. When it gets into gas, it goes to the compressor being compressed. So when the gas being compressed, it's high temperature and high pressure. That goes to condenser. So basically the condenser and evaporator, these two things are just heat exchangers. For a heat evaporator, it exchanges heat with some refrigerated space. So you have the cool temperature, so low temperature of refrigerants going through. But in the condenser, because it's a very high temperature, so it also naturally transfers heat with like the outdoor environment. So that's how it rejects the heat to those environments that you are going to have the heat rejected to. So that's a basic schematic of this system. And so if we could understand that part, we could watch a video. So we have 4 components of this system, and usually we will say it starts with the point when it gets out of this evaporator. So you can, if you're not very familiar with this system, you can say evaporator could be your indoor environment, and the condenser is the outdoor environment. So when your refrigerant gets evaporated, so it becomes a vapor state. So the vapor state would go into the compressor and being compressed. So you could see if a gas, a compressible gas being compressed, so of course the pressure gets high and also the temperature gets high. So with this very high pressure and high temperature of refrigerant vapor gets into the condenser, it just naturally rejects its heat to the environment. So this temperature would be much higher than like outdoor environment, say like 30, 40. But as long as you have a higher temperature, you could release your heat to the environment. So that's what happened in the condenser. So in the condenser, when we say like condensation is a phase change. So phase change is from the vapor to liquid, but there is no temperature change. So what temperature you're coming in, and ideally would be the same temperature comes out. There is only phase change. So you will have this same temperature and also same pressure, because there is like the friction inside this one would be really negligible. So we would say temperature the same, pressure the same. It's just the vapor has changed into a liquid phase and continues to this cycle. So, sorry, you can see, oh yeah, you can see the mouse. So now with only these three components, evaporator, compressor, and condenser, then you can see this cannot form a cycle, because if you have this high temperature and high pressure liquid goes to this evaporator again, it cannot absorb the heat from the indoor environment because temperature is high. Maybe temperature is just higher than this environment you want to refrigerate. So that's why we have to add something in between this process to make this liquid a low temperature liquid. In that way, when the low temperature liquid passes through the evaporator, it can naturally absorb the heat and gets evaporated. So in that process, by passing through some necessary parts, the part actually works to make the high pressure liquid to low pressure liquid is called this expansion valve. So you might have actually learned this thing in the thermodynamic course, but it's a different cycle, this Carnot cycle. But the basic components are the same. You need an expansion valve to make the liquid being expanded, pressure released, and temperature gets low. So after this valve, your refrigerant liquid has changed to a low temperature, and the temperature must be much lower than the indoor air temperature. So that's why your refrigerated space is transferring heat to this refrigerant, and so it continues this cycle again. So this video will, I guess it will have a final look, so you can have a look at this process. And through this schematic, what do you need to know? Because this only shows how it works, but what the principle behind the important ones would be in the evaporator and condenser, there is no temperature change because there is only phase change from liquid to vapor or vapor to liquid, ideally. So now the problem would become how do you quantify the heat transfer in those processes? Because we want to know how much heat has been removed from this space or being rejected to another space. So that's why you need this pH diagram. So what's showing on this slide is a simplified one. You have the pressure and the enthalpy. So this curve, so this curve represents the saturated state. So every point you find on this curve, on the left-hand side is saying it's a saturated liquid, and on the other side, on this line is saturated vapor. Yes?
Yeah, before you said that in the condenser, the pressure and temperature stays constant.
Yes.
But then, should it be rejecting heat?
Yes, it is rejecting heat. So you just imagine like 0 Celsius degree, you have water and ice, right? So you might have learned here, I don't know, at some stage. You have both ice and water at the same temperature, but if you want the ice to be melted into water or the water to be, so if it's melting, that means the ice must absorb some energy, so it melted into water. But in that phase change state, there is no temperature change. But that amount of energy you absorb is similar here. You need to release some heat to have the vapor change the state to liquid, or the evaporator to change the phase. And so those part, maybe it's in thermodynamics, is called sensitive heat and latent heat. For sensitive heat, you have the change of observable temperature change. But for latent heat, there is only phase change, but there is no temperature change. But you actually have this amount of energy change, and which will be reflected in this pH diagram. Is that clear? Okay. So we would say normally we call this part coming out of the evaporator as point 1. So that's on this pH diagram. On this right-hand side, that's saturated vapor. And when it goes past through this compressor, it's being compressed. So when it comes out, just maybe in the middle. Anyway, it's the same. That's point 2. So from point 1 to point 2, if you draw a line here, you can see it changed from pressure 1 to pressure 2. So that's what happened in this compressor. And in this process, change the color. In this pH diagram, you can also look at this, the charts as given to you, where you have this constant temperature would be the orange color. So it's quite close to a vertical line and horizontal line and goes to a curve. So the orange line would represent a constant temperature. So that would be temperature T2, and for 1 would be T1. So here you could see T2 here on this saturated line would be equal to T3, and T1 would be equal to T4. So this part is what I am mentioning earlier. I was saying every dot on this line is representing saturated state. So on the left-hand side, inside this space, it's subcooled region, and on the right-hand side, it's superheated region. In the middle, it's a mixture of both liquid and gas. So you could see in the middle, the temperature is constant. That's representing from the liquid to the gas. It needs a process to have this material to change from completely saturated liquid to completely vapor, which is saturated vapor. So within this process, you would observe no temperature change, but actually you will absorb amount of heat is in between these two. So if you know, let's change the color. So if you draw a vertical line, that will be your enthalpy value, H2. You can read from the table, or you find from the chart. And another point 3, you also draw a vertical line, and that is H3. So I would say the enthalpy change between 0.3 and 0.2 would be H2 minus H3 simply. So all those things you can find from the table or those charts. And here, this delta H. So the question is, from the delta H, can you know the Q dot heat transfer rate? How to do that? Yeah. So you find the enthalpy is kilojoules per kilogram. So that's the energy content of a system. So obviously, you could know the mass flow rate of the refrigerant. So that's usually kilograms per second, m dot, and times delta H, which is kilojoules per kilogram. Then you will get this Q dot. M dot times delta H. And that gives you kilojoules per second, so that's kilowatts. And that amount of energy, like in different process, you will know. For example, from I just finished this cycle here. I just listed 0.2 that's coming out of the compressor, so that's here. And then coming out of this condenser, 0.3, is a process that we say there is no pressure change, because obviously there is nothing to have a huge pressure friction to make it lose this kind of pressure. So we would say from 0.2 to 0.3, constant pressure, very easy to find where the points are, because you just draw a horizontal line where you find 0.2. And when it get across with this saturated liquid, it is the ideal state we want. So we say we find this state. Ideally, it will all the vapor will be cooled down and not really cooled down, like rejected the heat and has the phase change from vapor to liquid. So you will observe no temperature change, because follow the orange line, the temperature is constant. So here at 0.3, it's still pressure 2 and temperature 2. And now the last step would just be from 0.3 to 0.4. So 0.4 is out of the expansion valve and the beginning of this evaporator. So between 4 and 3, ideally, if we could find some expansion valve that can only reduce the pressure of this liquid, and there is no energy loss through that one. So from 0.3 and 4, you can see the pressure just changed from P2 to which pressure we just don't say that, but it must follow this line of constant H. So there is no energy loss, so we must draw a vertical line through that. So when you draw this vertical line, that H4 equals to H3, and also a horizontal line from 0.1, because we say there is only phase change, no temperature change, so you can find 0.4. So that's how, starting from 0.1, you get 2, 3, and 4. And this 4 process consists of this refrigeration cycle. And just as you observed, you can calculate the Q dot for each process by finding out what's the enthalpy difference. So for evaporator, the amount of heat being absorbed by the evaporator would be the amount of H1 minus H3. And the compressor would be H2 minus H1, so that is the work input from this compressor. And in the condenser, it's the sum of these two, so that's H2 and H3. So basically that's the cycle. We will do some practice later to help you understand this part. But so far, anyone get any questions? No? All good? So, okay. So now we could look at all these components one by one. So for the compressor, and it's just like a mechanical device, so not really related to what we're introducing in this course. So you just need to know for compressor, the function of it in this refrigeration cycle is to compress the gas. So we know from the evaporator we have this refrigerant vapor. So the gas is more compressible and it could be compressed to high pressure and high temperature. So that's a function of the compressor in this refrigerant cycle. And after that, you will have condenser. So condenser and evaporator, they are both heat exchangers. So you only later, you know, you have 2 weeks on heat exchangers. So maybe in those 2 weeks, you will learn better of how the heat exchanger works. But now, since it just listed, there are several types of heat exchange. So you can have heat exchange between liquids or between liquids and air. Now, a simple question. So you could see for the water-cooled heat exchanger and air-cooled one, we say the water-cooled is more common by using tube-in-tube and shell-in-tube. And for the air-cooled one, we prefer using tube and fin type. I guess it's better to give you some time to think about why we have this difference. So basically in heat exchangers, we have learned in heat transfer that like for heat transfer between inside tubes, so if it's constant surface temperature, we use HA delta T ln. That's for convection. For the water-cooled, we prefer like tube-in-tube or shell-in-tube. It basically provides less frictions. Because if you want the water to move through all these heat exchangers, you have the work input. If you have very huge friction, you need like more, like a larger pump. So maybe that's not preferable. So that's why like we prefer tube-in-tube or shell-in-tube. But for air-cooled one, you might notice the air and the water would have different fluid properties. So under the same velocity, the water always have a higher Reynolds number. So the heat transfer coefficient would be relatively higher. So that means in air-cooled heat exchangers, your H value is limited by these properties, always a little bit lower. So we cannot do anything to improve this part, so we can only increase the contact area between between one side to the other side. So that's why like fin types is basically you have a tube, but you have many things to increase the surface area of that one. In that way, you have better heat transfer coefficients. No, better heat transfer effectiveness. So, yes?
Can you talk us through which one is tube-in-tube and shell-in-tube?
Yeah. So this one is the tubes inside the shell. So it didn't draw this shell for you because if it has a shell, maybe you cannot see the tubes. But basically for this one, it's similarly like this. So you have many tubes inside this one, and you have a big shell on that. So you have fluid flow from one hand, and you have the other liquid flow through the other side. And for these things, it's actually kind of fins by you could see the surface area of the tubes has been increased. But you can also imagine for this part, if you use that on the water side, you could produce a lot of frictions on this side. So that's why it's more, you can use this for air because we want the surface area to be increased, and also like the friction is not that large by utilizing this one. And also for this one, it's kind of a combined, you have the tubes, that's the tubes, and also the vertical ones are fins. So that's mainly increased surface areas for the air-cooled heat exchangers. So there are lots of things, because we have already learned principles, but when you are looking at, for example, looking at these slides, you should not only like say, I just memorize this thing. You need to understand why we use these different ones. So you could actually see the reasons behind that. Okay, so is this part good? Questions? No? Okay. Okay, so basically these two slides we just finished introducing the components. So now we will proceed to see what's the calculations about the refrigeration cycles. And this is something from thermodynamics. I hope you don't get too confused with this part. I will go quickly go through these two slides because this is only the vapor power cycle. So this is not the refrigeration cycle. You just need to look at this. But we need to propose, or need to show this first, because later in the refrigeration cycles, our calculation is quite similar to this part. So just to quickly go through this vapor power cycle, it's used to like convert the heat to work power. So you will have the Q hot, so from the boiler, and that's being converted to the work net out and also the Q cold. So you will see this energy balance would be the Q hot consists of this work out, the total work and plus the Q cold. So in this way, if we want to find out what's the efficiency of this system, we might be just wondering how much work output you can provide by providing this heat. So if we define this efficiency, they just use the work output divided by the total input. So that's some idea or the form that we want the equations to be look like. And if you manipulate this one with the information, the energy balance, you know from that, you can get the efficiency of this cycle expressed as 1 minus Q cold divided by Q hot. And from a TS diagram, that you know the amount of Q cold is actually the surface area covered by this curve, and the Q hot is covered by this Q hot area. Anyway, so that's the concept in this thermodynamics. So they say that the Q cold divided by Q hot will be equal to also the ratio of the temperatures. So that's the basic idea of how you define this efficiency and how you find out this or calculate this efficiency by knowing temperatures or heat transfer rates. So that's some earlier, some knowledge from these earlier courses. And now, if we still try to utilize a similar format of analyze, then still with this refrigeration cycle, as we said, evaporator, that's 0.1, 2, 3, 4. And you can find the Q dot by looking at the enthalpy difference, delta H. So if you utilize that, that would be the evaporator is absorbing some heat, so it's taking away the heat from the space you want to refrigerate. So that's Q cold. And when it comes to the compressor, we are providing this work input to compress this vapor, this refrigerant vapor. So you know the energy balance would be Q cold plus W equals to Q hot, or the net work input equals to Q hot minus Q cold. So that's the basic energy balance we need to know from this one. And also, similarly to how they define efficiency, is we want to know what's the output on the input. So because it's a refrigeration cycle, so we want to know how much cooling power this cycle could provide compared to the work input. So you just utilize Q code divided by the work input. That is the definition of coefficient performance. So you need to know, like, firstly, energy balance, and secondly, this definition is important, but later we will do calculations on that. So if you also manipulate this equation, then you will see it's calculated just from the Q code and Q hot, which you can find from the delta H from evaporator and delta H from condenser. So the calculations for this cycle is actually quite simple, as long as you know where these 4 points are. And also it could be expressed by the temperature of the cold environment, which is the cold environment, and the temperature of the hot environment. So that's a coefficient of performance for refrigeration. Another concept is heat pumps. But as we said, heat pumps, you just reverse the direction, or you just think you swept these two places. For example, in winter, the indoor environment is actually the condenser side, and the outdoor environment would be the evaporator side. So it might take time for you to fully understand all those. So, but now we are just introducing these cycles for you. And do you get any questions on this part? No? Yeah, but I just think you do really need some time to go through all these cycles and figure out which part is on which side. Okay, so that's the calculations. So I just jumped these two slides is because I mainly explained how this works in the video slide. So you can have a little bit read about this one, but we actually already explained this part. So we did spend a large amount of time saying which is constant pressure, which one is phase change, so you have constant temperature, but you also have energy change. That is because all those understandings is important for you to find where these 4 points are. Okay, so if we stay on this one, this COP value, I'm not sure for the products here, but I know for all the products back in China, they must label these COP values on all these air conditioners. So of course, COP value, the higher, the better, because that means you provide higher cooling power. But now here I have a question. So what if you find a product that the COP value is low, or in the operations you find out the COP value is really low? Where could possibly go wrong, or what would be the issues for this system? If we just talk about temperatures.
The environment that it's in, the temperatures of the
Indoor?
environment?
Yeah. If the indoor environment gets lower, the performance gets better or worse?
Is it cooler?
Yes, it's cooler because we turn down the temperature. But you can bring in a lower T code because that's the environment temperature. What if you have a lower T code? What's the performance look like?
Worse.
Worse, yes, correct. So that's some analysis you can utilize here. So basically, it's also quite understandable in real life. So if you turn down the air conditioners to a much lower temperature, of course you want it just to be cooled down. But you could imagine that might consume much higher power usage. So this part can be reflected in the pH diagram as well. So in this process, if you move this dot of 1 to a lower place, then basically, firstly, you know, COP value of this cycle is the ratio of this part to this part when you have the values. But if you have a lower cold temperature, the point moves down, so this part becomes smaller and the work input is much higher. So that means you want the temperature to get lower, so you need a much higher input, but it's not creating a proportionally increasing cooling capacity. So when your COP gets down, that means this product is not a good one. So we would really want to keep or design some product that have better COP values. And on the other hand, if you have a higher hot temperature, which is the environment you are rejecting the heat to, so if the outdoor environment is really hot, you could also see anyway. So if this temperature is really hot, the lower part gets increased, and you also have a worse coefficient of performance. So this COP value matters in terms of, like, in the future, like every government is appealing for sustainable development. And especially like for all the commercial or public buildings, the HVAC system energy consumption is almost like 15% of the total energy consumption. So it would be really great that you do a little bit to increase the coefficient of performance, and that would save a lot of running cost for all those HVAC systems. So this is basically the answer to that question. So when your COP decreases, it might be because you have this cooler cold temperature or a higher hot temperature on different sides, on the evaporator or the condenser side. Okay. Yeah, we might could take a 10 minutes rest and go back and continue the rest of it.